Here we have a triangle ABC. We have a segment BD inside of this triangle, which is angle bisector. And we know the lengths of the segments AB, BD, and BC. And we ask to find the length of a segment DC. Today we're going to solve this problem in two ways. First way is geometrical way, the other involves more algebra, so you can compare and see which one you like better. First, like in many problems like this, we start with angle chasing. So on the very top, angle B is split in two congruent angles. Let's call them alpha. Now if you look at the triangle ABD, that's an isosceles triangle, so the angles at the base should be the same. Both of them are going to be 90 degrees minus alpha over 2. But that means that the angle right here equals 180 minus this angle. So this angle will be this. And the last thing we can do, we can find the angle C based on the other angles, and we can easily find that it's 90 degrees minus 3 alpha over 2. Now we found all the angles, we don't see anything unusual. But really the fact that AB equals to BD and they are the same kind of make me think, well, that's probably for a reason. And one thing I like to do is to draw circles. So for here, I can actually see that if I create a circle with a center at point B and with the radius of 6, this circle is going to go through point A, point D, and eventually it's going to cross the side BC at some point E. Obviously, BE is going to be the radius. So it's going to be equal to 6, and that would mean that EC will be 2. Now we connected D and E. And now, if you look at this picture, you find that the triangle DBE is identical to the triangle ABD. They're congruent. Now if we look at what we got two extra triangles. So let's continue our angle chasing. Now the angle right here, angle D in the triangle DBE, should be the same as angle A right here. So it should be also 90 degrees minus alpha over 2. And that means that the angle right here, angle EDC, has to be alpha. But now if you look at the big triangle DBC, and a small triangle ECD, you find those triangles have two congruent angles. So there is angle alpha here and angle alpha here, and they both share the angle C. So those triangles have to be similar. And on similar triangles, ratio of the respective sides should be the same. From that we can get this relationship. I just want to go in a little bit more details to explain how we get this relationship. So first of all, what we need to do is to pick up a pair of congruent angles. So for example, we can pick up this angle alpha in the big triangle and this angle alpha in the small triangle. And we're going to write the ratio of the sides that lay opposite of the congruent angles. So the side opposite of this angle alpha will be DC. The side opposite of this angle alpha will be EC. And that's what we have here. In a similar manner, we can pick up another angle. For example, we can pick up this angle D in the big triangle. The angle that is congruent to this angle in the small triangle is this angle E. The side opposite of this angle D is BC, and the side opposite of this angle E is DC. And that's what we have here. Now if you plug the numbers, we get an equation with respect to DC, which we can easily solve and find that DC equals to 4. So we're done with this problem. Now let's look at another way, how we can solve this problem. First of all, we're talking about sides, we're talking about segments, and we see that there is a bisector BD. So that should immediately tell us something about angle bisector theory. That actually says that this bisector BD splits the side AC in two segments, and the ratio of these segments equals to the ratio of two other sides of the triangle. So AD to DC will be equal to AB to BC. And that equals to 3/4, which means that if we say that AD equals to 3y, where y is unknown for now, DC has to be 4y. The next thing I see here is that we have two triangles, ABD, the left triangle, and the right triangle, DBC. We know two sides of each of those triangles. We know the angles between them are congruent. And we are looking for the third side. And that kind of reminds me of law of cosines. For the triangle ABD, law of cosines says that this side AD squared equals to a side AB squared plus side BD squared minus 2 times AB times BD times cosine of the angle between them. In a similar manner, we can write law of cosines for the triangle DBC. Now notice, if you look at these three equations, we find for these three equations we have three unknowns. We don't know AD, we don't know DC, and we don't know cosine alpha. And we can find them all from these three equations. Now, in our case, all we care about DC, so let's just concentrate on that. We already used the first equation. We already used angle bisector theorem when we said that AD is 3y and CD is 4y. Now let's plug those values in these two equations. Also, let's plug AB, BD, and BC in these equations. So the first law of cosines gives us this. The second law of cosines gives us this. What we're going to do now, we're going to express cosine alpha from both of these equations. That's what we're going to get. This expression is from the first law of cosines, and this guy is from the second law of cosines. Now what we have here is a linear equation for y squared, which we can easily solve to find that y squared equals to 1, which means that y equals to 1, and DC is 4y, that is 4. So, and now we have it. We have two ways how we can solve this problem. You can choose which way you like better. Obviously, the first way seems to be easier once we know how to do this additional construction. There's less math involved. But if you think carefully, you'll find that the first method, relying heavily on the fact that triangle ABD is an isosceles triangle. The second method doesn't care about this. In fact, we can apply the second method if these sides have different lengths. Now you know two ways how to solve this problem, but if you can come up with your own way, a third way, fourth way, fifth way, leave a comment.